Hello, this is Discrete Maths, MATH1081, and we're having a look at selection of problems out of Chapter 3. So this one is a very short one, but I want to say a little bit more about this problem, about these things called perfect numbers. This question just says, show there exists a perfect number. Well, we'll check what a perfect number is. So a perfect number is a number which is the sum of its own divisors. But we exclude itself, because it's always obviously divisible by itself, so we're going to exclude itself. So a perfect number is a number which is the sum of its own divisors. Well, how do we show there exists a perfect number? Well, we have to remember from primary school or junior high school or something, or playing around with numbers, that 6 is an example of a perfect number. So the solution to the problem is, that's it, 6. You could almost get away with just writing down 6 and get full marks. You've shown it's a perfect number. Well, you've written it down. I've shown there exists one, but I should write some English. So 6 is perfect, since if you take the factors of 6, excluding itself, you get 1 and 2 and 3 are the factors of 6, and you add them together and you get the number you start with. So 6 is a perfect number. Now that's it. That's actually the solution to the problem, and that's full marks. 6 is a perfect number since it's the sum of its. I found a number, I've shown there exists one by actually demonstrating one. But obvious questions arise when you see this, and the obvious question is, are there any other ones? Are there other perfect numbers? And in fact, let me say other examples are, well, 28, it turns out, is the next perfect number, because you add up the factors of 28, you get 1 plus 2 plus 4 plus 7 plus 14. And if you add those numbers up, that's 3, that's 7, 14, you get 28. So that's rather nice. 28's the next perfect number. The next one is 496. 496 is the next perfect number. I won't write down all the factors of it, but I leave you to check. If you write all the factors of that number, you end up getting back to 496. The next one is 8,128. And I won't write any more of them down because I can't remember what the next one is. Some interesting observations about it, however. Notice that all the perfect numbers I've written down, and I've written down the first 4, they all end in 6 and 8. In fact, they alternate, 6, 8, 6, 8. Well, lots of questions arise. Where did you get these from? How do you construct these numbers? Is there a nice simple way of finding these numbers? And secondly, do all the perfect numbers end in 6 and 8? All of these numbers are all even. Are there any odd perfect numbers? Do they alternate 6, 8, 6, 8? By the way, notice there's one with 1 digit, one with 2 digits, one with 3, one with 4. Does the pattern continue? So lots of interesting questions arise, and I'm going to tell you as much as is known about the answers to these questions. Firstly, I want to show you how to construct these, and I want to find a nice formula for actually constructing these even perfect numbers. This goes back to the ancient Greeks, in fact. It's a fairly natural thing to do to write down the powers of 2. So I'm going to write down 1, and I'm going to write down 2. 2 squared is 4, 2 cubed is 8, and then 16, 32, 64, and so on. So these are all the powers of 2. And you can imagine the ancient Greeks having slaves to do all their work for them. An ancient Greek mathematician might have written down these numbers and started playing with them. And in particular, what they did was they started to add them. So 1 plus 2 gives me 3. And I now multiply by the last number in my head. And so the last number in my head, 1 plus 2 is 3, and the last number in my head was 2. So I multiply these together and I get 6. Well, big deal. You happen to get 6. It happens to be the first even perfect number. Well, what happens if I keep going? If I add the next number on, so I get 1 plus 2 plus 4. By the way, you can just add these two because that's already the sum of those. So you get 7, and you multiply 7 by 4, and you get 28. And now you start to get more excited because you see that that's another one of these perfect numbers, 28. Well, you keep going and say, well, I'll add on the next one. So that plus that gives me 15. And if you multiply that by that, well, whatever you get, it's not very interesting. It doesn't give you a perfect number. That's a shame. Anyway, as often in maths, persevere. So let's try the next one. So 16 plus 15 is 31. And indeed, if I multiply 31 by 16, I get 496. And there's the next even perfect number. Well, you keep going. Here you get 63. Well, you multiply that by that, you get a number. Turns out not to give you a perfect number. But if you keep going, that plus that gives me 127. And if I multiply these two together, once again, I get 8,128. And you can keep going with the pattern. You can keep adding and multiplying and see what happens. And notice that sometimes you get these even perfect numbers, and sometimes you don't. Sometimes you get numbers here that just doesn't work. You multiply that by that, it doesn't give you a even perfect number. So no perfect number there, no perfect number there. And you ask yourself the question, well, why is it working for some of the numbers? Why does that one, that one, that one, and that one work? But why do these ones not work? And if you stare at the numbers for a bit, you might begin to realise then that these numbers, 3, 7, 31 and 127, these are all rather special because these numbers are all prime numbers. Whereas these ones are not prime. These numbers are not prime. So we feel, I'm not proving anything here, but we feel a sort of result coming on here. We feel a theorem coming on that this method will give you even perfect numbers provided the numbers you get here are not prime numbers. Are prime numbers. Let me write down exactly what we've done here. So in calculating this, what did we do? We added up the powers of 2. So writing this down algebraically, we took 1 plus 2 squared, and we're going to stop after n terms. So that'll be up to 2 to the n minus 1. So we take 1 plus 2 plus 4 up to, I take n terms, I stop there, and we multiplied by 2 to the n minus 1. We multiplied by the last number we had in our list. So this sum in here represents these numbers along the bottom here. And this is a nice geometric series, and I can sum this. Best to sum it this way. First term is 1, common ratio 2. There are n terms. So this is 2 to the n minus 1 divided by 2 minus 1, which is 1. So I can sum this geometric series, and I get that nice little formula. Now remember, this only worked if these numbers were prime. So we need this. This is an even perfect number. Is an even perfect number if this 2 to the n minus 1 is prime. And you might like to have a look back in your problems there and have a look at question 15a. And you'll see there that problem was about looking at when a number like this is prime, and it turns out that the number n up here has to be prime. So you should have a look back at that problem 15a there. Now I'm not proving this here, I'm just stating a conjecture. So we conjecture that this sum equals that is an even perfect number if this 2 to the n minus 1 is prime. And actually that's not very hard to prove, because if this is prime, then you can write down all the factors of this. The factors of this will be 1 plus 2 all the way up to 2 to the n, or they will be that times 1 and 2 all the way up to 2 to the n, and you can simplify that, and if you do that you'll find you end up with twice this one. And then if you subtract it off, you'll get back to this one again. So I'll leave you to check that. I've just made a conjecture here. You can give a proof of that. That's a nice exercise to do. Well, what are the other things we said? Well, I said that all of these even perfect numbers end in 6 and 8. Well, they do. So so here are some facts. Every even perfect number ends in 6 or 8, and that's not very hard to prove using this formula here. Is the converse true? Is it true that if you've got an even perfect number, then it must have this form? And the answer to that is yes. So every even perfect number has the above form. So this formula completely characterises all even perfect numbers. If this is prime, then this is an even perfect number. If you've got an even perfect number, it must look like that, and that's got to be prime. And that's harder to prove, that last result. So that's harder to prove. Do they alternate 6, 8, 6, 8, 6, 8? The answer is no, they don't. They all end in 6 or 8, but they don't necessarily alternate. The Greeks said there was one with 1 digit, one with 2, one with 3, one with 4, and so on, and that's also false. I think the next one after this certainly doesn't have 5 digits in it. It's bigger than that. You've got to go further along here. There's still lots of unsolved problems about perfect numbers. How many of these are there? We don't know. Are there infinitely many? That's an unsolved problem. It all depends on how many primes there are of this form, and the answer is we don't know how many primes of this form there are. So these are rather interesting numbers. You can Google perfect numbers and find out more information if you're interested in that, but that's all I've got to say on this problem.